Good day, students! Welcome back to Maestrang Techy YouTube channel. We are now in quarter 4 of our grade 9 science lesson. And the first topic that we are going to have today is all about the horizontal and vertical motions of a projectile. Check out our learning objective. Describe the horizontal and vertical motions of a projectile. Get ready to learn this lesson, so keep on watching! In grade 8, you have learned about Newton's second law of motion, the law of acceleration. According to this law, the net force is equal to the product of the mass of the object and its acceleration. Let's have a simple activity to refresh your mind. State the second law of motion by completing this paragraph. So, let us start. The law of course, acceleration. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. That is the second law of motion. Good job, class! It is very good that you can still recall the law of acceleration. Always remember that the larger the force applied on an object, the larger its acceleration. Usually, the acceleration of a body may change and vary from time to time due to several factors. If that is the case, when can we say that there is a constant acceleration? Let's have a review about uniformly accelerated motion, or UAM. Look at the picture shown in your screen. Are you familiar with these blue uniformed men who are usually positioned in the busy streets? You might have seen them as you cross the streets to reach your school or on your way to the market or a friend's house. They are the traffic enforcers. Who are they and what do they do? They play a crucial role in maintaining the flow of traffic and in implementing laws and rules and regulations on the road that every motorist should follow. They may also be considered as frontliners amidst the COVID-19 pandemic as they assist soldiers and police officers in checkpoints. Speed limits are observed on roads. They vary and depend on several conditions. Speed limits for highways are different from speed limits on small avenues and streets. This prevents vehicles to speed up or accelerate unnecessarily in our busy streets, as they are being monitored by traffic enforcers. Acceleration is defined as the rate of change in velocity with time. It is a vector quantity having both magnitude and direction. Acceleration of vehicles usually changes from time to time. A vehicle may speed up as it travels to highways or slow down as it approaches an intersection. It should also help when the stoplight is red and eventually accelerate when the light turns green. We can say that most type of acceleration that we observe is not constant or non-uniform due to these factors. When you are riding a vehicle, you can say that speeds up or slows down based on its speedometer. A speedometer indicates the speed of a vehicle. It is usually combined with a device known as odometer that records the distance traveled. Assume that you are riding a vehicle and observe these speedometer readings. What can you say about the readings on the speedometer during each minute? What can you infer from the data in the table? This means that vehicle speeds up. Every minute, there is 1 km/h increase on the speed of the vehicle. The increase for every minute is constant. Therefore, we can say that the vehicle has uniform acceleration. This vehicle exhibits a uniform or constant acceleration. It is a type of motion in which the velocity of an object changes by an equal amount in every equal time period, just like this example. In uniformly accelerated motion, or UAM, the value of the acceleration is constant. It does not change. The velocity changes, but at a constant rate. An object with zero acceleration is said to be in uniform motion. An object in uniformly accelerated motion has non-zero but constant acceleration. Acceleration represents how velocity changes with time. Velocity represents how position changes with time. Next picture. As you can see, we have a coin. Toss it upward. Does it stay up? No. When it reaches its maximum height, eventually it will go down. What makes it go down? The answer is gravity. Gravity pulls the coin down. Things that are thrown upward will go down because of this force. Gravity also pulls us towards the earth. That is why we are not being thrown outside the space. What floor was your classroom when you were in grade 7 and grade 8? Was it on the 3rd or 4th floor? Which is easier, climbing to your classroom or going down to the school canteen? When you climb a high place, you go against gravity. When you are on a high place and you go down, you are moving toward gravity, so you use less force. Same is true with free-falling objects. Objects at free fall also exhibit uniformly accelerated motion. The acceleration due to gravity is 9.8 meter per second squared, neglecting air resistance. It is a constant acceleration for all falling bodies, regardless their mass and weight. All objects on the Earth's surface are being accelerated towards the center of the Earth at a rate of 9.8 meter per second squared. This means that if you raise an object above the surface of the Earth and drop it, the object will start from rest and its velocity will increase 9.8 meter per second. For each second, it is falling toward the Earth's surface until it strikes the ground. In general, a uniformly accelerated motion is the one in which the acceleration of a body throughout the motion is uniform. It can be observed in either vertical or horizontal dimension and in 2 dimensions. Let us have an activity for you to understand the uniformly accelerated motion. Analyze each scenario. Identify if it exhibits uniformly accelerated motion or not. Let us have the first photo. A bike at rest. Is this UAM or not? The answer? Not UAM. Next. A fruit dropping from a tree. Is this an example of UAM or not? The answer? UAM. Next. A boy holding a book. And the answer? Not UAM. Next. Rocks falling from a cliff. Is this a uniformly accelerated motion or not? The answer? UAM. Last picture. A truck running with a constant acceleration. Is it UAM or not? The answer? It is an example of UAM. Great job, class! You did well! Now, let us proceed. Let us take a look at this photo. As you can see, it is a photo of a man diving. The motion of the man as it dives into the water is moving along a curved path due to a natural force called gravitational force or gravity. Gravity is a natural force that causes objects to fall towards the earth. Hence, the acceleration due to gravity is always directed downwards. With this, the motion of the man undergoes projectile motion. Projectile motion is a form of motion where an object moves in a curved path. The object that is thrown or projected and exhibits projectile motion is called projectile. The curve-like path undertaken by a projectile is called trajectory. Let us have another photo. Are you familiar with this game? A sepak takraw player kicking a rattan ball over the net. What is the projectile in that scenario? If you think that the rattan ball is the projectile, then you are right. How do you describe its trajectory? The rattan ball traveling on a curved path. That is correct. In mathematical terms, we call this pattern parabola. An angle-launched projectile exhibits a full parabolic trajectory motion. This shows that as the player kicks the rattan ball in the air, the ball will eventually go back to the ground still due to gravity as it moves horizontally. Hence, projectile motion consists of horizontal and vertical motion working independently. The two pictures and scenarios that I have shown you are the two types of projectile motion: horizontally launched projectiles and angle-launched projectiles. Let us take note of their components. In horizontal motion, it is the X component. No resistance in any form. To simplify, we neglect air resistance. Next, there is a constant horizontal velocity. We use Vx to represent it. V for velocity and X for horizontal component. Next, horizontal acceleration is 0. Why? Because there is no external force acting along the horizontal motion. It means that acceleration does not exist. And it is represented as AX, A for acceleration and X for the X component. Next, we call the horizontal distance as range, and it is represented as dx. D for distance and X for the horizontal component. Now, let us go to the vertical motion. This is the Y component. The force acting upon in this motion is the force of gravity, and it is represented as G or AY, or acceleration in the Y or in the vertical motion, or acceleration due to gravity. The constant acceleration is always equal to negative 9.8 meter per second squared. Take note, class, that negative indicates the direction, and the direction is downward. Due to the presence of gravity accelerating at 9.8 meter per second squared, this caused the vertical velocity to increase, which makes it not constant, and it is represented as Vy. V for velocity and Y for the vertical component or vertical motion. Next, we call the vertical distance as the height, and it is represented as H or dy. For you to understand more, let us have an example scenario. This is an example of a horizontal launched projectile. Suppose you roll a marble on a frictionless table. Observe the motion of the marble as it goes down the floor. The motion of the marble is gradually increasing from point A to point B. Due to the presence of gravity accelerating at 9.8 meter per second squared, this caused the vertical velocity to increase, which makes it not constant. For the horizontal velocity, there is no external force acting along the horizontal motion, which means no acceleration, resulting to a constant horizontal velocity. Let us have an example problem to solve. A marble is thrown horizontally from a tabletop with a velocity of 1.50 meter per second. The marble falls 0.70 meters away the table's edge. Find the following. How high is the table, and what is the final velocity of the marble just before it hits the cup? First, let us illustrate the problem. A marble is thrown horizontally with an initial velocity of 1.50 meter per second. We are going to represent it as Vi, or initial velocity. Next, the marble falls at 0.70 meter away from the table. Therefore, we can say that it is the horizontal distance or dx, and that is again 0.70 meters. Next, we are going to find how high the table is, or our vertical distance or dy. And also, if we have initial velocity, of course we have the final velocity of the marble before it touches the cup, and it is represented as Vf, or the final velocity. Now, let us solve the problem. Here are the given and the formulas that we are going to use. Again, our given, the horizontal distance is 0.70 meters, our initial velocity, which is equal to 1.50 meter per second, and our acceleration due to gravity is 9.8 meter per second squared. To find the height or the vertical distance of the table, this is our formula. Get the 1/2 of the product of acceleration due to gravity and the squared of time. As you can see, we do not have the value of time. Therefore, we need to get first the time to get the height of the table. So, take note of this formula. Let us substitute our given to our formula. Time is equal to dx, which is 0.70 meters, divided by the initial velocity, 1.50 meter per second. Let us divide 0.70 divided by 1.50, and the answer is 0.47. This is already rounded off. Next, how about the unit? As you can see, we can cancel out meters. So let's cancel out meters, and the remaining unit is second. Therefore, our final answer is 0.47 second. Now, we can determine the height of the table. Let us substitute the given in our formula. Acceleration due to gravity times time, which is 0.47. Do not forget to get the square of the time, divided by 2. Squaring 0.47, we get 0.2209 seconds squared. Next, let us simplify this by multiplying the acceleration due to gravity and time. Therefore, we have 2.16482 divided by 2. As you can see, we can cancel out seconds squared, and the remaining unit is meters. Next, let us divide this into 2, and the quotient is 1.08 meters. This is also rounded off. Therefore, this is our final answer. The height of the table is 1.08 meters. Now let's proceed to our next question. What is the final velocity of the marble just before it hits the cup? As you can see, we have an additional given that we got a while ago, which is the height or the vertical distance, 1.08 meters. To determine the final velocity of the marble, we need to get its resultant velocity or VR. The resultant velocity of an object is the sum of its individual vector quantities. Remember that final velocity has two components, the horizontal and the vertical. So let us find the two velocity components and then solve for the resultant velocity using the Pythagorean theorem equation. To get the value of Vfy, this is the formula that we are going to use. Take note, class, that Ag is similar to G. So, let us substitute the given to our formula to find the value of Vfy. 2 times acceleration due to gravity times the height. Multiplying these three quantities, we have the product of 21.168 meters squared per second squared. Let us get the square root. Vfy is equal to negative 4.6 meter per second. As you can see, we also simplify the unit. Take note, class, that negative sign indicates downward direction. So, we can say that VFY is equal to 4.6 meter per second downward or negative 4.6 meter per second. Now that we have the value of VFY, we can now determine the final velocity or the resultant velocity. Let us go to the next slide. Again, this is our formula, the Pythagorean theorem equation, square root of VFY squared plus VFX squared. We already have the value of VFY, which is negative 4.6 meter per second. Now, to get the value of Vx squared, take note, class, that initial velocity is also equal to the initial horizontal velocity and the final horizontal velocity, which is also equal to the horizontal velocity. Therefore, the value of Vfx is 1.50 meter per second. Now, let us substitute the given to our formula. Vr is equal to the square root of negative 4.6 meter per second squared plus 1.50 meter per second squared. Getting the squared of these two quantities, we have 21.16 and 2.25. As you can see, we also squared the unit. Add these two, we have 23.41 meters squared per second squared. Get the square root, and our final answer is 4.84 meter per second. And this is our final answer. And that is how you are going to solve this kind of problem. Take note, class, of these equations that may help you solve problems involving projectile launched horizontally. And that ends our lesson this week. Check out the part 2 of this lesson. Before we end, let us have a shout out. Shout out to OGZ Vlog. Shout out to Gab Kalugdan. Shout out to Cree Tom. Also, shout out to Ma'am Marisol Marfiel. And shout out to Bayawan City Science and Technology Education Center, Negros Oriental. Thank you all so much for watching. I really appreciate it. If you like, share, subscribe, and comment down below for a shout out. See you guys on my next video. Bye!